What causes a supernova? There is an event happening somewhere in the observable universe right now that will release more energy in 10 seconds than our sun will produce across its entire 10 billion year existence. Not more energy per hour, not more energy per year, more energy total in 10 seconds. And the thing that causes it isn't a collision. It isn't a bomb. It isn't something crashing into a star from the outside. It's something happening on the inside. Something going wrong. Something failing so catastrophically, so completely, and so inevitably that once it starts, nothing in the known laws of physics can stop it. Tonight, you're going to understand exactly what causes a supernova. Not just the surface answer, not just a star blows up, but the real answer. The physical answer. The answer that starts millions of years before the explosion and ends in a fraction of a second. The answer that reveals why supernovae aren't accidents. They're not random catastrophes. They're the predetermined conclusion of a process that begins the moment a massive star is born. By the end of this, you'll understand what drives a star toward explosion from its very first breath. Why certain stars are condemned from birth while others die quietly, and what specific chain of events transforms a living, shining star into one of the most violent explosions the universe is capable of producing. If this kind of deep exploration is something you value, a quick like or subscribe genuinely helps the channel keep going. It costs you nothing, and it makes a real difference. Now let's get into it. The fundamental setup. To understand what causes a supernova, you need to understand something about stars that most people never really grasp. A star is not a stable object. It is not sitting calmly in space, radiating light the way a light bulb sits on a table. A star is a dynamic, continuous battle between two opposing forces. Those forces are in constant tension every single moment of the star's life, and a supernova is what happens when one of those forces finally wins. The first force is gravity. Gravity is the inward force. It is always trying to compress the star. Every atom in the star has mass, and mass creates gravity, and that gravity pulls everything toward the center. A star like the Sun contains roughly 2 × 10⁻³ kilograms of material. All of that material is gravitationally attracted to every other piece of material. The net result is a constant, relentless inward squeeze. Gravity doesn't negotiate. It doesn't take breaks. It has been trying to crush the star since before the star was born, and it will keep trying until the star is dead. If gravity were the only force at work, every star in the universe would collapse to a point almost instantly. The sun would shrink to a dense ball in a matter of minutes. But gravity isn't the only force at work. There's a second force pushing back. That force comes from the core of the star, where temperatures and densities are so extreme that atomic nuclei are being smashed together and fused into heavier elements. This process, nuclear fusion, releases enormous amounts of energy. That energy heats the material in the core, which creates pressure, which pushes outward against the inward squeeze of gravity. These two forces, gravity pulling in and fusion pressure pushing out, are in a constant, dynamic equilibrium. When the forces are balanced, the star neither collapses nor expands. It holds its shape. It shines steadily. Astronomers call this balance hydrostatic equilibrium, and it is the defining condition of a stable living star. The Sun has maintained this balance for about 4.5 billion years. It will maintain it for roughly another 5 billion. Most of the stars you can see on a clear night are in hydrostatic equilibrium right now, quietly burning their fuel, keeping gravity at bay. But here's the thing you need to understand at a deep level. This balance has a condition, a requirement, a price. The outward pressure only exists because fusion is happening. Fusion only happens when there is fuel. When the fuel is gone, the pressure disappears. And when the pressure disappears, gravity wins. That's the fundamental cause of a supernova. Not a collision, not an outside force. The cause is internal. The cause is a star running out of the fuel it needs to fight gravity. And gravity doing what gravity has always been doing, collapsing everything inward. But not every star dies this way. The story depends almost entirely on one variable, mass. Why mass is everything? Stars come in a staggering range of sizes. Some have barely enough mass to sustain fusion at all. Others contain dozens or even 100 times the mass of the Sun. And this difference in mass is the difference between a quiet death and a cataclysmic explosion. Take our Sun. It's a modest, middleweight star. When it eventually exhausts the hydrogen fuel in its core in about 5 billion years, it will expand into a red giant, puff off its outer layers in a glowing shell of gas, and leave behind a small, dense remnant called a white dwarf. No explosion, no catastrophic collapse, just a slow, graceful fade. The Sun simply doesn't have enough mass for the story to go any further. Now take a star with 15 or 20 times the mass of the Sun. Everything changes. The greater mass creates greater gravitational compression on the core. Greater compression means higher temperatures. Higher temperatures mean fusion proceeds faster and at higher energy thresholds. The star burns hotter, brighter, and far more quickly than smaller stars. You might expect a more massive star to last longer because it has more fuel, but the opposite is true. The additional mass doesn't just add more fuel, it turns up the burning rate by an enormous factor. Luminosity, the energy output of a star, scales roughly as the cube or fourth power of the star's mass. So a star 20 times the mass of the Sun doesn't shine 20 times more brightly. It shines tens of thousands of times more brightly. And because it's burning its fuel at that vastly accelerated rate, it exhausts that fuel far sooner. The Sun will spend around 10 billion years fusing hydrogen in its core. A star with 20 solar masses will burn through its core hydrogen in roughly 10 million years. A star that is 100 times the mass of the Sun might exhaust its hydrogen in under 3 million years. In cosmic terms, these massive stars are mayflies. They blaze with almost incomprehensible brilliance, and then they die, spectacularly. The very property that makes them so luminous, their enormous mass, is also what drives them toward explosion. More mass means more gravitational pressure. More gravitational pressure means hotter cores. Hotter cores means faster burning. Faster burning means running out of options sooner. And running out of options, as we'll see, means supernova. This is why massive stars, and only massive stars, die as supernova. The threshold is roughly 8 times the mass of the Sun. Below that, the core never gets hot enough or dense enough for the chain of events that leads to catastrophic collapse. Above it, the star is locked into a trajectory from birth that ends in one of the most violent events the universe produces. Let's follow that trajectory in detail. A massive star's life is a sequence of fuel stages, each one buying time against gravity. Each new stage requires higher temperatures than the last, burns faster than the last, and produces less energy per reaction than the last. The whole sequence is an accelerating countdown, and understanding it is the key to understanding what causes a supernova. Hydrogen burning is the first and longest stage. In the cores of all stars, including massive ones, the dominant fusion process fuses 4 hydrogen nuclei, essentially 4 protons, into a single helium nucleus. In the process, about 0.7% of the original mass is converted directly into energy, according to Einstein's famous mass-energy relationship. This is why fusion is so powerful as an energy source. You don't need much mass conversion to produce colossal amounts of energy. In a star 20 times the mass of the Sun, hydrogen burning lasts roughly 10 million years. That sounds like a long time, but the Sun will spend 1,000 times longer doing the same thing. The massive star burns its hydrogen in a geological eye blink. When core hydrogen is exhausted, fusion stops in the center. Without fusion pressure, the core begins to contract under gravity. But this contraction itself releases gravitational energy, heating the core. That heat ignites hydrogen fusion in a shell surrounding the now dead core. And the core keeps contracting, keeps heating, until it reaches temperatures of roughly 100 million degrees. At that point, the next fuel can ignite. Helium burning begins at 100 million degrees. The process is called the triple alpha reaction because it requires 3 helium nuclei, also called alpha particles, to collide and fuse in a sequence to form carbon. The reason this requires so much more heat than hydrogen burning is that helium nuclei each carry 2 protons compared to 1 for hydrogen. More protons means a stronger positive electrical charge, and like charges repel each other. You need vastly more kinetic energy to smash helium nuclei together hard enough for the strong nuclear force to grab hold. The triple alpha process is genuinely remarkable. 2 helium nuclei first combine to form beryllium-8. But beryllium-8 is extraordinarily unstable. It exists for only about 10 to the -16th seconds before it disintegrates back into 2 helium nuclei. That's less than 1/10 of a quadrillionth of a second. A third helium nucleus must collide with that beryllium-8 within that impossibly tiny window to form carbon-12. The probability of this happening in any single interaction is vanishingly small. But inside a stellar core, where trillions upon trillions of helium nuclei are colliding every fraction of a second, it happens continuously. Carbon accumulates. Some of that carbon then absorbs another helium nucleus to produce oxygen. Helium burning therefore yields 2 of the most fundamental elements for life: carbon and oxygen. In a massive star, helium burning lasts about 1 million years, 1/10 of the hydrogen burning lifetime. The clock is already accelerating. When helium in the core is exhausted, the same pattern repeats. Fusion stops. The core contracts. Temperatures rise. Eventually, a new threshold is crossed, and the next fuel ignites. Carbon burning requires roughly 600 million degrees. Carbon nuclei have 6 protons each, so the electrostatic repulsion is substantial. The reactions produce a mix of neon, sodium, and magnesium. In a massive star, carbon burning lasts about 1,000 years. 1,000 years compared to 10 million for hydrogen. The acceleration is dramatic. Neon burning comes next, at around 1.2 billion degrees. This stage is peculiar because it begins not with direct fusion, but with photodisintegration, a process in which extremely energetic photons, gamma rays, are energetic enough to shatter neon nuclei apart into oxygen and helium. The freed helium nuclei are then captured by remaining neon to build magnesium. Neon burning in a massive star lasts only a few years. Oxygen burning requires temperatures near 1.5 billion degrees. Oxygen nuclei carry 8 protons each, requiring tremendous energy to fuse. The primary product is silicon, along with sulfur and several other elements. Oxygen burning lasts somewhere between half a year and a full year, less than 12 months. Look at the progression. Hydrogen, 10 million years. Helium, 1 million. Carbon, 1,000 years. Neon, a few years. Oxygen, less than a year. Each stage is roughly 1,000 times shorter than the one before. The star is hurtling toward its own destruction, with each successive fuel burning away faster and more furiously than the last. And then comes the final stage. Silicon burning ignites at around 3 billion degrees. Silicon nuclei have 14 protons each, and the electrostatic barrier to direct fusion is enormous. What actually occurs isn't clean, direct fusion. Instead, high-energy photons shatter silicon nuclei apart, releasing alpha particles, which are then rapidly captured by other silicon and heavier nuclei in a cascade of reactions. Silicon builds to sulfur, sulfur to argon, argon to calcium, calcium to titanium, titanium to chromium, chromium to iron. Each step adds an alpha particle, moving up the periodic table toward heavier and heavier elements. Silicon burning lasts approximately 1 day. In some stars, as little as a few hours. 1 day. The star spent 10 million years burning hydrogen. It spent 1 day burning silicon. The entire arc of the star's life, from its ignition to its final hours, has been a relentless acceleration toward this moment. And when silicon burning ends, it produces something the star cannot use, something that changes everything. It produces iron. Iron is the reason supernova happen. Specifically, iron 56 is the reason. And to understand why iron is so catastrophic for a massive star, you need to understand something about nuclear binding energy. Every atomic nucleus is held together by the strong nuclear force. The amount of energy required to completely dismantle a nucleus into its individual protons and neutrons is called the binding energy. But binding energies don't just tell you how tightly held together a nucleus is. They also determine whether fusion releases energy or consumes it. For every element lighter than iron, fusing nuclei together produces a more tightly bound product. The product is more stable than the ingredients. The excess stability is released as energy. This is the entire basis of stellar fusion. The star fuses lighter, less stable nuclei into heavier, more stable ones, and the energy difference powers the star. But iron 56 sits at the absolute peak of nuclear stability. It is the most tightly bound nucleus that exists. There is no heavier nucleus that is more stable than iron 56. This means that if you try to fuse iron into anything heavier, you don't produce a more stable nucleus, you produce a less stable one. Instead of releasing energy, the reaction requires energy. It absorbs energy. It is endothermic. Fusing iron doesn't push outward against gravity. Fusing iron would actually steal energy from the star, worsening the situation rather than helping it. Think of it this way. The star has been like a person burning progressively lower quality fuel to keep a fire going. First, they burned seasoned oak, which burned long and hot. Then damp logs, which burned faster and produced less heat. then green wood, which burned faster still, then cardboard, then paper, then old furniture, then the floorboards themselves. Each fuel more desperate than the last. Each one bought less time. Each one required more of it to produce the same warmth. Now the person is holding a piece of iron and realizing that no matter how they position it, no matter how much heat they apply, no matter what they try, iron doesn't burn. It can't burn. It will never burn. The fire goes out, and without the fire, the cold that was always waiting outside finally gets in. That's exactly what happens in the core of a massive star. Silicon burning ends, iron accumulates, and the star has no fuel left that can fight gravity. What makes iron's position so final, so absolute, is not just that it can't be fused profitably. It's that the star arrived at iron by following the only path physics allowed. Every stage of fusion, from hydrogen all the way up through silicon, released energy by moving toward greater nuclear stability. Iron is the destination of that journey. There is nowhere else to go. The star didn't make a mistake. It didn't take a wrong turn. It did everything correctly. It burned every available fuel with perfect efficiency. And after millions of years of doing so, it ended up exactly where physics always intended it to end up, staring at an iron core and having no answer for gravity's question. The iron core grows over hours and days as silicon burning in the surrounding shell continues adding material to it. The core is supported temporarily not by fusion, but by electron degeneracy pressure, the same quantum mechanical phenomenon that supports white dwarfs. This is a consequence of the Pauli exclusion principle, which states that no two electrons can occupy the same quantum state simultaneously. When matter is compressed to extreme densities, electrons are packed so tightly that they resist further compression purely out of quantum mechanical necessity. This resistance doesn't depend on temperature, it depends on density. Electron degeneracy pressure can hold the iron core together, but only up to a point. That point was calculated in 1930 by a 20-year-old Indian-American astrophysicist named Subramanian Chandrasekhar during a sea voyage from India to England. He worked out the mathematics of electron degeneracy and determined that it can only support a stellar core up to approximately 1.4 times the mass of the Sun. This is called the Chandrasekhar limit. As silicon burning continues in the shell surrounding the iron core, more and more iron is deposited onto the core. The core gets heavier. It creeps toward the Chandrasekhar limit gram by gram. And the entire time, the temperatures in and around the core are climbing toward levels that trigger the next disaster. When the core temperature exceeds roughly 5 billion degrees, two processes kick in simultaneously, and both of them are catastrophic. The first is photodisintegration. At 5 billion degrees, photons carry so much energy that they can shatter atomic nuclei. Those gamma rays begin bombarding the iron nuclei in the core, breaking them apart into helium nuclei and individual neutrons. This process absorbs energy, an enormous amount of energy. The destruction of a single iron nucleus into 13 helium nuclei and 4 neutrons requires about 124 million electron volts. When you consider that trillions upon trillions of iron nuclei are being destroyed every microsecond, the energy drain becomes staggering. In mere milliseconds, photodisintegration absorbs the equivalent of the energy the star produced, over hundreds of thousands of years of previous burning. It's like opening a catastrophic drain in the thermal reservoir that was keeping the core from collapsing. The energy that was supporting the star against gravity is suddenly consumed. The second process is electron capture, sometimes called inverse beta decay. At the extreme temperatures and densities of the collapsing core, electrons are forced into close proximity with protons. The conditions favor a reaction where an electron combines with a proton to produce a neutron and a neutrino. The neutrino immediately escapes the core, carrying energy away. And crucially, each electron that disappears removes a small amount of electron degeneracy pressure. The very force that was holding the core up is being systematically dismantled from within. These two processes together constitute a death spiral for the iron core. Photodisintegration drains thermal energy. Electron capture drains degeneracy pressure. Both processes remove the forces keeping the core from collapsing. Both processes accelerate as the core heats and compresses further, which then accelerates both processes more. It's a feedback loop with no escape valve. The core has been creeping toward the Chandrasekhar limit, while silicon burning added mass from above. Now it receives this double assault from within. At some point, which can be calculated quite precisely in modern stellar models, the iron core crosses the limit. Electron degeneracy pressure fails, and gravity, which has been waiting for billions of years for exactly this moment, takes over completely. What happens next occurs in less than 1 second, but it is one of the most violent seconds in the history of any star. The inner core begins to fall inward, not gradually, not gently, instantaneously and catastrophically. There is no longer any force balancing gravity. The material accelerates freely inward under one of the strongest gravitational fields in the universe. Within milliseconds, the inner core, a region containing roughly 0.6 to 0.8 solar masses, is falling inward at speeds approaching 70,000 kilometers per second. That is roughly 23% of the speed of light. Nearly a quarter of the maximum speed anything can travel in the universe. Imagine a sphere roughly the size of the Earth, containing more mass than the entire Sun, imploding at 23% the speed of light. The violence of this is genuinely beyond any analogy from ordinary human experience. The most powerful nuclear weapons ever built by humanity release energy on the order of 10 to the 17th joules. The energy released during this collapse exceeds that by factors that make the comparison meaningless. These are different categories of event, not merely different magnitudes. The outer core follows, collapsing slightly behind the inner core. Above that, the star's outer layers begin raining inward as well, responding to the sudden disappearance of pressure support from below. The entire central region of the star is in free fall. The inner core alone goes from a diameter of roughly 8,000 kilometers to a diameter of approximately 30 kilometers in less than half a second. That is a linear compression factor of over 250. In terms of volume, the compression is roughly 15 million to 1. An Earth-sized sphere of material is being squeezed into a ball about 30 kilometers across in less time than it takes to blink. The density during this collapse climbs from around 100 billion kilograms per cubic meter to values that simply don't exist anywhere else in the universe except inside neutron stars and black holes. At the extreme end of the collapse, the density reaches something like 200 to 300 quadrillion kilograms per cubic meter. To put that in human terms, a teaspoon of this material would weigh approximately 1 billion tons. More than every road, every building, every ship, every vehicle ever constructed by humanity, compressed into a volume smaller than a sugar cube. As the density climbs toward these extreme values, something extraordinary happens. The individual neutrons and protons in the collapsing core are squeezed so tightly together that they are no longer separated by meaningful space. They are essentially touching. The core has reached nuclear density, the density that exists inside atomic nuclei themselves. Except instead of being a single nucleus containing a few hundred particles, this is a ball of nuclear matter 30 kilometers across, containing more particles than any nucleus that has ever been described by nuclear physics. At nuclear density, the strong nuclear force, which normally operates only across distances smaller than an atomic nucleus, becomes relevant across the entire inner core. And the strong nuclear force at very short distances is not attractive. At very short distances, when nuclear matter is compressed beyond its natural density, the strong force is repulsive. It pushes back. This is the core bounce, and it is the trigger for everything that follows. The inner core has been collapsing at nearly a quarter the speed of light. It encounters the wall of nuclear repulsion from the strong force, and it stops. Not gradually, almost instantaneously. In less than a millisecond, the infalling inner core goes from a collapse velocity of 70,000 kilometers per second to essentially zero. The deceleration is the most violent in the known universe. And just like a super ball thrown against a concrete floor, the inner core doesn't just stop. It bounces. It rebounds outward. This outward rebound launches a powerful compression wave into the surrounding material of the outer core, which is still falling inward. That compression wave rapidly steepens into a shock wave, a supersonic discontinuity that moves outward through the infalling material like an expanding wall of force. On one side of the shock, material is still falling inward. On the other side, material is being pushed outward. The shock is essentially a collision between the outward moving rebound pressure and the inward moving material of the outer core. If the shock could simply plow through the entire star, energetically enough to reverse the fall of all the material above it and blow the outer layers into space, you'd have your supernova. Simple, clean, direct. Core collapses, bounces, shock blows up the star. Early models of supernova predicted exactly this. The so-called prompt shock mechanism assumed the bounce was energetic enough to drive the explosion directly. For a while, this seemed plausible. It isn't what actually happens. The shock wave, born from the core bounce, is powerful. But it is not powerful enough. Not quite. As the shock moves outward through the outer core, it runs into material that is still falling inward. To drive a supernova, the shock doesn't just need to stop this material. It needs to reverse it, accelerate it outward to escape velocity. Every gram of infalling material that the shock encounters saps its energy. The shock has to push all of that material against the flow of a gravitational field that is still extremely powerful. But there is an even more devastating energy drain on the shock. Photodisintegration strikes again. The shock heats the material it passes through to billions of degrees. At those temperatures, the iron and silicon nuclei in the infalling outer core are shattered by the high-energy photons the shock itself creates. Disintegrating those nuclei absorbs energy directly from the shock. The outer core contains several tenths of a solar mass of iron and silicon, and breaking each nucleus down requires absorbing energy that the shock cannot afford to lose. The numbers are brutal. The shock starts with roughly 10 to the 51st ergs of kinetic energy from the core bounce. Each tenth of a solar mass of iron that the shock dissociates absorbs roughly 10 to the 51st ergs. The math tells the story. The shock barely has enough energy to disintegrate even a fraction of the infalling material before it runs out of steam. Within about 10 to 20 milliseconds after the bounce, the shock wave has lost most of its energy. It decelerates, it slows further, and somewhere between 100 and 200 kilometers from the center of the newly formed proto-neutron star, it stalls. The infalling material above it keeps piling on. The shock is being pushed back slightly. It sits there, not advancing, not retreating, suspended in a precarious stalemate. The supernova has failed, or so it appears. This was one of the deepest puzzles in astrophysics for decades. Every computer simulation of core collapse ended the same way. The shock stalled. If the simulations were correct and nothing intervened, the infalling material would simply keep adding to the proto-neutron star until its mass exceeded the limit neutron degeneracy pressure could support. Then the proto-neutron star would collapse into a black hole. No explosion, no scattered elements, no supernova remnant, just a star winking out of existence and leaving nothing but darkness. But we know supernovae happen. We observe them regularly. We've detected their neutrinos, their light, their expanding remnants, their gravitational waves. Something must revive the stalled shock. Something must inject enough energy behind it to push it through the rest of the star. The question was, what? The answer came from an unexpected source. The most elusive particles in physics, neutrinos. To understand why neutrinos matter here, you first need to understand what's happening at the center of the collapsing star. The proto-neutron star left behind by the core bounce is not cool. It is not quiet. It is a ball of nuclear matter roughly 20 to 30 kilometers across, containing more than a solar mass of material, and its internal temperature exceeds 100 billion degrees. At these temperatures, thermal processes produce neutrinos in colossal quantities. Electron-positron pairs annihilate into neutrinos. Plasmon processes generate neutrinos. Neutron-proton interactions produce neutrinos. The proto-neutron star is radiating neutrinos from every cubic centimeter of its volume, in all directions, at rates that strain comprehension. The total energy emitted in neutrinos over the first few seconds following core collapse is approximately 3 times 10 to the 53rd ergs. To put that number in context, it is roughly equal to the total energy output of the Sun across its entire 10 billion year lifetime, released in a matter of seconds. It is 50 times the kinetic energy of the explosion itself. The visible light from a supernova, which can temporarily outshine an entire galaxy of hundreds of billions of stars, represents less than 1% of 1% of the total energy budget. A supernova is, at its core, a neutrino event. The spectacular light show we observe is a footnote. Under ordinary circumstances, neutrinos barely interact with anything. They can pass through a light year of solid lead without hitting a single atom. In normal matter, they are essentially invisible. But the region behind the stalled shock is not normal matter. The densities there, while far lower than inside the proto-neutron star itself, are still enormously high by any terrestrial standard. And at these densities, neutrinos have a small but real probability of being absorbed. When a neutrino is absorbed by a neutron, it converts the neutron into a proton and an electron, depositing its energy into the surrounding material. When a neutrino is absorbed by a proton, it produces a neutron and a positron, also depositing energy. These absorption events are rare individually, but the number of neutrinos streaming outward from the proto-neutron star is roughly 10 to the 58th in the first few seconds. If even 5 to 10% of those neutrinos deposit their energy in the region immediately behind the stalled shock, the total energy deposited is enough to reheat that material, raise its pressure, and slowly push the shock outward again. This is the neutrino-driven mechanism, and it is the leading explanation for how most core-collapse supernovae produce their explosions. The process isn't instantaneous. It takes hundreds of milliseconds, sometimes close to a full second. The neutrinos gradually heat the material behind the shock. The pressure builds. Eventually, the shock, which had stalled and appeared defeated, begins to move outward again. Slowly at first, then faster as it encounters less dense material at higher altitudes in the star. It is worth pausing on how counterintuitive this is. The neutrino is often described as the most antisocial particle in nature. It barely acknowledges the existence of ordinary matter. Particle physics experiments routinely involve detectors buried in mountains of shielding material specifically to block out every other kind of particle, and neutrinos pass right through all of that shielding as if it simply weren't there. And yet here, in the specific environment behind a stalled supernova shock, those antisocial particles are the heroes of the story. They are the energy source that saves the explosion, the very property that makes them useless as an energy carrier under normal conditions. Their near total indifference to matter is precisely what allows them to carry energy out from the deep core without being absorbed prematurely. They deposit just enough energy in just the right zone to tip the balance between a failed collapse and a successful supernova. It is one of the stranger and more beautiful accidents in all of astrophysics. But there is a complication. In the simplest, most symmetrical version of the supernova calculation, treating the star as a perfect sphere with everything happening uniformly in all directions, neutrino heating alone often isn't quite sufficient. One-dimensional, computer simulations, even with correct neutrino physics, frequently fail to produce robust explosions. The shock gets pushed a little but then stalls again. Something is missing. What is missing turns out to be turbulence. When astrophysicists began running supernova simulations in 2 and 3 dimensions, allowing the collapsing material to move asymmetrically, to develop swirls and plumes and irregular flows, the picture changed dramatically. Two specific phenomena emerge in these multidimensional simulations that are crucial for driving the explosion. The first is convection. You've seen convection in everyday life. Heat water in a pot, and the hot water at the bottom rises while cooler water sinks to take its place, creating a churning circulation. Behind the stalled shock, exactly the same physics operates. The material nearest the proto-neutron star absorbs the most neutrino energy and becomes buoyant. It rises outward toward the shock. Cooler material near the shock sinks inward toward the proto-neutron star, gets heated by neutrinos in turn, and rises again. This convective circulation acts like a thermal conveyor belt. Without convection, heated material sits between the neutron star and the shock, slowly radiating its energy away without doing useful work. With convection, that heated material is continuously carried up to the base of the shock, where its pressure can push the shock outward. Cool material is continuously brought down to the heating region, where it can absorb more energy. The whole system becomes far more efficient at converting neutrino energy into outward mechanical pressure on the shock. Convection can increase the efficiency of neutrino energy deposition substantially. The second phenomenon is called the standing accretion shock instability, abbreviated SASI. It is a large-scale, low-frequency oscillation of the shock front itself. Instead of remaining a perfect sphere, the shock begins to slosh. It bulges outward in one direction while contracting in another. This sloshing grows over time, developing into violent, asymmetric oscillations of the entire shock surface. The shock wobbles and surges like a water balloon being shaken. SASI amplifies turbulence in the region behind the shock. It creates large-scale asymmetries in the flow of material. These asymmetries are important because they allow the shock to expand preferentially in certain directions, while material continues to fall inward from others. The shock doesn't need to push uniformly outward against the entire infalling column. It can find the weakest point, push through there, and establish an expanding hot bubble that gradually takes over. The combination of neutrino heating, convection, and SASI transforms the dynamics behind the stalled shock. Three-dimensional simulations running on modern supercomputers consistently produce successful explosions when all three effects are properly included. The physics is still not perfectly understood. There are genuine uncertainties in how neutrinos interact with dense nuclear matter at proto-neutron star densities, but the broad framework is established. Neutrino heating is the energy source. Convection and SASI are the amplifiers that make the energy transfer efficient enough to revive the shock. Together, they drive the explosion. Once the shock is revived, what happens in the next few seconds is one of the most spectacular sequences of events in the universe. The shock accelerates outward through the star. It has traveled outward from the central proto-neutron star and is now moving into the star's overlying layers. The shells of silicon, oxygen, neon, carbon, helium, and hydrogen that accumulated over millions of years of sequential burning. These layers have been completely unaware of what was happening in the core. The core collapse, the bounce, the stalled shock, the neutrino heating. All of this occurred in the innermost 200 kilometers of a star that might be hundreds of millions of kilometers across. The outer layers were still fusing their elements, completely oblivious. Now the shock arrives. The shock heats each layer it passes through to billions of degrees, and at those temperatures, explosive nuclear burning begins. This is not the steady, controlled fusion of a living star. This is explosive nucleosynthesis, fusion on a timescale of seconds rather than centuries. As the shock tears through the silicon and oxygen layers, it drives fusion reactions that produce vast quantities of nickel-56, along with iron, sulfur, and other heavy elements. As it moves through the carbon and oxygen shells, it produces more neon, magnesium, and silicon. The shock is not merely blowing the star apart. It is cooking the material as it passes, forging elements that will eventually find their way into planets and living things. The entire outer envelope of the star, several solar masses worth of material spanning from the edge of the collapsing core all the way to the surface, is picked up by the shock and flung outward. The ejection velocities range from a few thousand to tens of thousands of kilometers per second, with some material moving at 5 or 10% the speed of light. The star's surface brightens as the shock breaks through. To an observer watching from a distance, the star suddenly blazes with a ferocity that can rival the combined output of every other star in its host galaxy. This is the optical supernova. This is what astronomers see when they observe a core collapse event. But it's worth remembering what we know. The core has already been gone for hours. The surface is only now discovering what happened below. The light from the explosion is sustained over weeks and months primarily by the radioactive decay of nickel-56. Nickel-56 is unstable. It decays to cobalt-56 with a half-life of about 6 days. Cobalt-56 then decays to iron-56 with a half-life of about 77 days. Each decay releases gamma rays that heat the expanding cloud of debris from the inside, keeping it radiating long after the initial blast has faded. This radioactive heating is the reason a supernova remains visible for months, rather than fading in hours. The explosion has torn the outer layers of the star away and hurled them into space. But at the center, something remains. Something extraordinary. The inner core that bounced, the proto-neutron star that powered the neutrino engine, doesn't disappear. It cools over the following seconds, minutes, and hours, primarily by emitting more neutrinos, contracting slightly as it cools, and settling into a final configuration. What it becomes is a neutron star. A neutron star is among the most extreme objects the universe contains. It holds between 1.4 and about 2 solar masses, compressed into a sphere roughly 20 to 30 kilometers across. The density throughout most of its volume is nuclear density or close to it. The density at its center may exceed nuclear density, reaching conditions where our understanding of matter becomes genuinely uncertain. The surface gravity of a neutron star is approximately 200 billion times Earth's surface gravity. The magnetic field of a typical neutron star is around 1 trillion times stronger than Earth's magnetic field, and the rotation rate of a newly formed neutron star, spun up by conservation of angular momentum during the collapse, can be extraordinary. The original stellar core may have been rotating once every few hours or days. When compressed by a factor of hundreds of thousands in radius, that rotation spins up by an enormous factor. Some newly formed neutron stars rotate dozens or hundreds of times per second. The fastest known pulsar, PSRJ 1748-2446 AD, rotates 716 times per second, with its equatorial surface moving at nearly 1/4 the speed of light. These rapidly rotating neutron stars with their powerful magnetic fields become pulsars, sweeping beams of radiation through space like cosmic lighthouses. When one of those beams sweeps across Earth during each rotation, we detect a pulse of radio waves arriving with machine-like regularity. But neutron stars are not the only possible remnant. If the original star was sufficiently massive, roughly above 25 solar masses, though this threshold is uncertain, the remnant core may be too massive for even neutron degeneracy pressure to support. Neutrons, like electrons, obey the Pauli exclusion principle and can provide degeneracy pressure. But this pressure also has a maximum. The Tolman-Oppenheimer-Volkoff limit sits somewhere between 2 and 3 solar masses, though the exact value depends on the equation of state of nuclear matter at extreme densities, which remains an open question in physics. If the remnant core exceeds this limit, nothing in known physics can stop the collapse. The core continues inward past neutron star density, past any density we can describe, and forms a black hole. A region of space-time where gravity is so extreme that no signal, no particle, no light can escape once it crosses the event horizon. Sometimes this happens in a two-stage process. A neutron star forms initially, but material falling back onto it from the explosion adds enough mass to push it over the Tolman-Oppenheimer-Volkoff limit, and it collapses into a black hole seconds or minutes after formation. In other cases, the stalled shock is never revived. No explosion occurs at all. The entire star simply falls inward and vanishes into a black hole in what astronomers call a failed supernova. There are now observational hints of this happening. Stars that were monitored then simply disappeared without any recorded explosion. Everything we have described so far is a core collapse supernova. It requires a living massive star. It requires an iron core. It requires gravitational collapse. It produces a neutron star or black hole remnant. But there is a second, entirely different mechanism by which stars can explode. It doesn't involve a massive star at all. It doesn't involve gravitational collapse. It involves a dead star, a stellar corpse that has been sitting quietly in space for billions of years. It involves a white dwarf. When a star with a mass like our sun exhausts its fuel, it sheds its outer layers and leaves behind a white dwarf, a ball of carbon and oxygen roughly the size of Earth, containing about half a solar mass, supported against collapse by electron degeneracy pressure. White dwarfs are dead. There is no fusion happening inside them. They simply radiate away their heat over billions of years. Left alone, a white dwarf is harmless. It will cool for trillions of years and eventually become a cold, dark object called a black dwarf, though the universe isn't old enough for any to have reached that stage. But white dwarfs are rarely left alone. Most stars exist in binary systems, two stars orbiting each other. When a white dwarf has a companion star, circumstances can arise in which material from the companion flows onto the white dwarf through a process called mass accretion. The companion may swell into a red giant and overflow its gravitational boundary, allowing material to stream toward the white dwarf. This material doesn't fall directly onto the surface. It carries angular momentum from the orbital motion and spirals inward, forming an accretion disk, a swirling, extremely hot disk of infalling gas. Gradually, material from this disk settles onto the white dwarf's surface, and gradually, the white dwarf grows heavier. Gram by gram, century by century, the mass of the white dwarf increases. As it approaches the Chandrasekhar limit of 1.4 solar masses, the density and temperature at the white dwarf center climb. The white dwarf is mostly carbon and oxygen. These are fusible materials. And at some point, the conditions at the core become extreme enough for carbon fusion to ignite. Here is where things become terrifying. In a normal star, there is a built-in thermostat. If fusion in the core gets more energetic, the core heats up, expands, reduces its density, slows the reaction rate, and restores equilibrium. The core adjusts. But a white dwarf is supported by electron degeneracy pressure, which doesn't depend on temperature. When carbon fusion ignites and heats the white dwarf's interior, the white dwarf doesn't expand to compensate. The density stays the same. The temperature rises freely. Higher temperature means faster fusion. Faster fusion means more energy. More energy means higher temperature. There is no negative feedback. Nothing applies the brakes. This is a thermonuclear runaway, a positive feedback loop with no off switch. Within seconds, the temperature climbs to billions of degrees. The fusion propagates outward through the white dwarf as a nuclear flame, consuming carbon and oxygen and converting them into heavier elements, primarily silicon, sulfur, and ultimately nickel-56. The energy released in a few seconds is staggering, roughly 1 to 2 times 10 to the 51st ergs of kinetic energy, enough to not merely blow off an outer layer, but to completely disintegrate the white dwarf. Unlike core collapse supernovae, which leave a neutron star or black hole behind, a Type 1a supernova leaves nothing. The entire white dwarf is consumed. Every gram of carbon and oxygen is burned. The explosion is total and complete. There is no remnant to find, no neutron star orbiting the site, no black hole marking where the star used to be. Just an expanding cloud of heavy elements, primarily nickel-56 and iron, racing outward into space. A second pathway to Type 1. A supernova involves not a white dwarf and a normal companion, but 2 white dwarfs orbiting each other. Over millions of years, these 2 dead stars spiral toward each other by emitting gravitational waves, the ripples in space-time predicted by Einstein's general relativity. As they spiral inward, they eventually merge. The combined mass of the merger can exceed the Chandrasekhar limit, triggering the same runaway carbon fusion. Same explosion, same total destruction. No remnant. Astronomers have found evidence supporting both pathways. Searches near the sites of known Type 1. A supernovae sometimes find a surviving companion star, supporting the accretion model. Other sites show no companion at all, supporting the double white dwarf merger model. The likely answer is that both happen in nature, contributing to the overall population of Type 1a events. Type 1. A supernovae have a property that makes them cosmologically invaluable. Because the explosion always involves roughly the same amount of material burning under roughly the same conditions, the total energy released and the total nickel-56 produced are roughly consistent from one event to the next. This means every Type 1a supernova reaches roughly the same peak luminosity. Not perfectly identical. There is variation. But in the early 1990s, astronomer Mark Phillips identified a remarkable regularity in that variation. Brighter Type 1. A supernovae fade more slowly after peak, while fainter ones fade more rapidly. By measuring the rate at which a Type 1a supernova fades, you can determine its true luminosity. Once you know true luminosity and measure apparent brightness, the inverse square law gives you the distance. This makes Type 1a supernovas what astronomers call standardizable candles. They can be seen across billions of light years, far beyond any other reliable distance indicator. In the late 1990s, 2 independent research teams used these cosmic rulers to measure how the universe's expansion has changed over billions of years. Both teams expected to find the expansion slowing down, gravity pulling the universe's content back together, decelerating the outward expansion left over from the Big Bang. Instead, they found the opposite. Distant supernovae were fainter than expected, meaning they were farther than expected. The expansion of the universe is not decelerating, it is accelerating. Something is pushing the universe apart faster and faster. That something has been named dark energy. We don't know what it is. We know it constitutes roughly 68% of the total energy content of the universe. We know it behaves like a repulsive pressure uniformly filling all of space, driving the accelerating expansion. We know it has been the dominant force shaping the universe's dynamics for about 5 billion years, but its physical nature remains one of the deepest open questions in science. The discovery of dark energy earned the Nobel Prize in Physics in 2011 for Saul Perlmutter, Brian Schmidt, and Adam Rees. And it came entirely from studying the deaths of white dwarfs, dead stars exploding billions of light-years away. Both types of supernova, the core collapse variety and the thermonuclear type 1a, contribute something irreplaceable to the universe: heavy elements, scattered into space to be incorporated into the next generation of stars and planets. The elements forged in a massive star's core over millions of years of sequential burning are locked inside that star when it's alive. They cannot leave. They cannot become part of a planet or a living cell. It takes an explosion to free them. The shock wave of a core collapse supernova tears through the stellar layers, ignites explosive nucleosynthesis, and flings several solar masses of enriched material into the interstellar medium. Hydrogen, helium, carbon, oxygen, neon, magnesium, silicon, sulfur, calcium, iron, and dozens of other elements are scattered across light-years of space. They mix with the interstellar gas. Over millions of years, gravity gathers some of this enriched material into new clouds that eventually collapse to form new stars and new planetary systems. Type 1a supernovae are thought to be the dominant producers of iron in the universe. The iron in your blood, the iron in the Earth's core, the iron in every steel structure ever built. Most of that iron was probably forged in the thermonuclear detonation of white dwarfs billions of years before the solar system existed. For elements heavier than iron, the one's fusion cannot produce, an additional process is required: neutron capture. In certain stellar environments flooded with free neutrons, nuclei can absorb neutrons faster than they can decay, building up heavier and heavier elements in rapid succession. This is the R process, responsible for producing roughly half of all elements heavier than iron, including gold, platinum, and uranium. For decades, core collapse supernovae were considered the primary site of R-process nucleosynthesis. More recent evidence from gravitational wave observations in 2017 suggests that mergers of two neutron stars, the remnants of two successive supernovae in a binary system, are at least as important. The kilonova produced in that merger showed spectroscopic signatures consistent with heavy R-process elements forming in the debris. Core collapse supernovae likely contribute as well, through neutron-rich winds blown off the proto-neutron star in the seconds after explosion. The full accounting of where each element comes from is rich and detailed. Hydrogen and helium from the Big Bang. Carbon and oxygen from helium burning in stellar cores. Elements up through iron from a combination of stellar nucleosynthesis and explosive nucleosynthesis in supernova. Elements heavier than iron from neutron capture in supernova and neutron star mergers. Every element in the periodic table has a specific cosmic origin, and supernovae are central to almost all of them. Your body is roughly 65% oxygen by mass. That oxygen was forged by nuclear burning in massive stars and scattered into space by supernova explosions billions of years before the sun formed. About 18% of your body is carbon, produced by the triple alpha reaction in stellar cores. The calcium in your bones was forged during explosive silicon and oxygen burning in supernovae. The iron in your hemoglobin was produced in silicon burning in massive stars and in thermonuclear detonations of white dwarfs. The phosphorus in your DNA was created during carbon and neon burning. The zinc, selenium, and iodine your body requires in trace amounts were assembled through neutron capture. These atoms drifted through interstellar space for hundreds of millions of years after the supernovae that created them. They mixed with other gas and dust in the galaxy. Gravity drew them into a new cloud about 4.6 billion years ago. That cloud collapsed to form the sun and the planets. The Earth formed from the material, and over billions of years, under conditions that are still not fully understood, those atoms organized themselves into molecules, into cells, into organisms, and eventually into creatures complex enough to look up at the night sky and ask where they came from. The answer, at its most fundamental, is supernova. Every heavy atom in your body traces back to a star that ran out of ways to fight gravity, or to a dead star that accumulated too much mass and ignited in a thermonuclear cataclysm. The atoms that make you up were freed by those explosions and eventually gathered by gravity into the Earth. They were always going to end up here, in some form, because that is the universe's process. Create, ignite, burn, explode, scatter, and create again. Let's be clear about the distinction between these two mechanisms, because while both are called supernovae and both produce spectacular explosions, they are fundamentally different events. A core collapse supernova requires a living, massive star of at least 8 solar masses. The cause is gravitational. The iron core grows to the Chandrasekhar limit. Electron degeneracy pressure fails. The core implodes, bounces at nuclear density, and the stalled shock is revived by neutrino heating to blow the star apart. A neutron star or black hole is left behind. The explosion scatters a mix of elements from hydrogen through the iron group. These supernovae occur in regions of active star formation because massive stars live short lives and die near where they were born. A Type 1. A supernova requires a dead white dwarf in a binary system. The cause is thermonuclear. Carbon fusion ignites under degenerate conditions when the white dwarf approaches or exceeds the Chandrasekhar limit through accretion or merger. A runaway reaction destroys the entire star. Nothing is left behind. The explosion produces primarily iron group elements. These supernovae can occur anywhere in a galaxy, including in old elliptical galaxies with no ongoing star formation, because white dwarfs are the remnants of stars that may have died billions of years ago. The same name covers two completely different mechanisms, two different causes, two different triggers. What they share is scale. Both produce roughly similar amounts of energy. Both briefly illuminate an entire galaxy with the light of a single dying star. Both scatter heavy elements into space, and both are woven into the fabric of everything that exists. Somewhere in the observable universe right now, a massive star is burning its final hours of silicon. An iron core is accumulating. The Chandrasekhar limit is approaching. Electron degeneracy pressure is holding on by a thread. The double assault of photodisintegration and electron capture has already begun in earnest. In hours, or perhaps in minutes from this very moment, that core will cross the threshold. Gravity will take over completely and finally and without appeal. The inner core will collapse to nuclear density in less than half a second, bounce, and launch a shock wave. The shock will stall, and then, powered by an unimaginable flood of neutrinos amplified by convective turbulence and the sloshing instability of the shock itself, it will be revived. The shock will tear through the star. The star will explode. We probably won't see it happen. It is likely too far away, too obscured by intervening dust, too faint by the time its light reaches our instruments. But it is happening right now, as you read this. The same process has been happening billions upon billions of times over the 14 billion-year history of the universe. Each time it happens, heavy elements are scattered into space. Each time, the universe becomes slightly richer, slightly more complex, slightly more capable of supporting the structures that lead to planets and chemistry and life. The stars had to die so that we could live. This is not a metaphor. It is the literal physical truth of our existence. The atoms in your body were liberated by stellar death. The planet beneath your feet was assembled from the scattered ashes of ancient explosions. The air in your lungs carries oxygen that was forged in stellar furnaces and released in catastrophic blasts before the solar system existed. A supernova is caused by a battle that has been going on since the first stars were born. Gravity versus everything else. When everything else finally fails, when the last fuel is spent and the last quantum mechanical defense fails, gravity wins. And in winning, it triggers an explosion so powerful and so complete that it reshapes the galaxy. Not just the galaxy, but eventually the planets, and the life on those planets, and the thoughts and the minds of the creatures those planets produce. The cause of a supernova, when you trace it back to its origin, is the most universal force in nature: gravity. Patient, inexorable, relentless. Every star is born fighting gravity. Every star spends its entire life fighting gravity. And every sufficiently massive star eventually loses that fight in a way that shakes the universe. But here's the thing about that defeat. It isn't quiet. It isn't small. When a massive star finally loses its war with gravity, the loss is so total and so rapid that the rebound produces one of the most energetic events the universe is capable of generating. The very act of losing releases more energy than the star accumulated across millions of years of steady burning. The defeat becomes the detonation. There is something almost philosophical in that. The star fought gravity for 10 million years. Every year of that fight was sustained by converting mass into energy, pushing back against the inward crush. The fight was real. The effort was genuine. The star was not passive. It was actively resisting, continuously. And when the resistance finally failed and gravity crashed inward and the core bounced back outward, all of that stored gravitational energy, all of the potential that gravity had been building up by compressing more and more mass into a smaller and smaller space, was released at once, in less than a second. The star didn't merely die. It converted the energy of its own collapse into an explosion that scattered the products of millions of years of nuclear burning across light years of space. Every carbon nucleus, every oxygen nucleus, every silicon and sulfur and iron nucleus the star ever produced was freed in that moment, liberated, sent outward at speeds approaching a significant fraction of the speed of light. And somewhere, tens of millions of years later, some of those atoms drifted into the right part of the galaxy at the right time and were swept into a collapsing gas cloud that formed a new solar system. Some of them became a rocky planet. Some of them became oceans. Some of them became the organic molecules that gave rise to living cells. Some of them, eventually, became the neurons in a human brain asking the question, what causes a supernova? Gravity causes it. Fuel exhaustion causes it. Nuclear physics causes it. The Chandrasekhar limit causes it. The iron-binding energy curve causes it. All of these are different ways of saying the same thing. The universe has rules, and stars that are massive enough eventually reach the end of what those rules allow. When they do, gravity wins. And when gravity wins that completely, the universe celebrates the victory with the most spectacular explosion it knows how to make. That's what causes a supernova, not randomness, not accident. A war that was always going to end this way, fought by a star that burned with everything it had for as long as it could, against a force that never stopped pressing. When the fuel ran out and the last defense failed, the star didn't just collapse and disappear quietly into the dark. It exploded. It scattered itself across space. It became the raw material for everything that came next. For new stars, new planets, new oceans, new chemistries, and new forms of complexity that the universe had never produced before, including us. Thank you for spending this time exploring one of the most profound processes in nature. If this kind of deep exploration is something you find genuinely valuable, a like or subscribe helps the channel continue making these journeys into how the universe works at its most fundamental level. And the next time you look up at the stars, remember, you are not just looking at light. You are looking at the furnaces that made you, burning across billions of years of darkness, turning gravity's inevitable victory into life's extraordinary beginning.